Welcome, students. So, in our previous classes, we have learned basics of matrices, may it be vector creation, addition, multiplication, as well as matrix addition, multiplication. All this we have already seen, along with some transformations. Today, we'll build upon these concepts and we'll try to solve system of linear equations. Now, before going to system of linear equations, you have to understand what it actually means um, by saying that you're going to solve the linear equations. So I'm going to use this slide from Deep Learning AI. This is very good website, as well as a slide prepared by Andrew Ng and his team. So where in which they have explained various concepts. You can check it out. Um, but because this slide can be used for educational purposes, we don't have any issues. We are going to use. Okay. So first of all, you have to understand what is meant by a linear equation and how a linear equation is obtained. How a real world scenario is converted into a linear equation. So let's just say you want to predict the power generation output based on a factor like wind speed. Then what you will do is you will start plotting the points at so and so speed, so and so wind speed. You had so and so power generation. Okay, something like that. You will plot on a 2D plot, and you will get these dots. Now, if you notice, these dots are following a particular direction, a straight line path, right? So, what I can do is, if I want to predict what would be the power output at wind speed, let's just say 12 meters per second, but we don't have the data point here. What I can do is I can simply extend this line above so that it meets at this 12 meter per second point, something somewhere here. Okay, and I can immediately calculate, I can compare the y value, y coordinate value, and I can immediately tell approximately, not exactly, because these are all probability values. Approximately or probably the value of power generation at wind speed 12 meters per second square is something like 6 or 5,500 kilowatts. Okay, so something like that. So basically the point is, with historical data, whatever the data that you have existing, you can extrapolate and predict the future outcomes. Okay, so here they have indicated, let m be some weight associated with wind speed, and b some error term, and power output is given by m into wind speed plus b. This is a straight line equation. Okay, so straight line equation is when you have one feature associated with power generation. Let's just say this is your x-axis, y-axis. Okay, so here if you want to predict the power, then you can multiply with slope, we call it slope. Okay, with along with the weight, and add a error term to predict the future values. Essentially what we are doing here in this entire process is, we are taking a feature and predicting the values. Now in this process there are 4 steps which I have shown here. First step is, you will already have y values and x values in this equation. Y is equal to mx plus c, or y is equal to mx plus b. Okay, you already have some data from the past. At so and so wind speed, so and so power was generated. Okay, that y values and x values are already there. Now if you somehow find out m and c, let's just say you somehow identified m value and c value by some calculations, then what you can do is, now you have complete value, no, you have complete y value, m value, x value, as well as some error term you have. And what you can do is you can ask the model to learn the patterns from these all the values. Upon learning the values, upon learning the patterns, in the future you can predict the y value basis on this learned m values and c values, and x values you anyway will have. Okay, so these steps, the step in which you train the model is called model training, and the step in which you find out the new y value is called as prediction. Okay, so here power output can be written as m into w plus c. Okay, so extending this concept here, okay, for multiple features, let's just say the power generation depends on various features like wind speed, temperature, okay, and pressure and humidity, etc. Okay, so these are some of the features. Then our equation will become w1 into feature 1, w2 into feature 2, w3 into feature 3. That way it goes to b. Here b, actually it has to be b1 plus b2 plus b3 plus b4, but because we are gonna use the error term as one single term, so we have indicated it as b, and this will be our output. Output is also called as target. Output here is power generation. Okay, so basically it became a linear equation. So essentially what you did was you took a real world scenario, converted into a linear equation. Okay, now this linear equation can be further represented in the form of a matrix. Okay, so let's just say your um, let me open this file one moment. So let's just say your equation is minus x1 plus 3x2 equals to 7, 3x1 plus 2x2 equals to 1. This can be represented in the form of minus 1, 3, 7, 3, 2, 1. Okay, either you can represent like this with only the coefficients, or you can split and represent using minus 1, 3, 3, 2, 7, 1. Okay, this way. Now, to solve these linear equations, okay, so which is essentially your data. Okay, uh, okay, let's say you have, for one turbine, this is the output. Let's just say you have n number of turbines, m number of turbines, then you have m number of linear equations. Humanly you can calculate one or two equations, right? But if you have so many linear equations, system of linear equations, you have to employ computer, no? And somehow if you convert this into, if you represent this into matrices, then you can simply do a dot product and get the result. Okay, which is what we do in the machine learning. So basically essentially you take all these equations, okay, and you convert them into, you represent them in the form of dot product of vectors which holds the intercepts along with a matrix which holds the x values. These x values are already known. Okay, x values are known. W values is something that you have to find out, and b value is something, b value you can ignore, it is the error. No system is 100% efficient. The maximum is 99.99 efficiency. Okay, and y values are also known. During training, y values are known, x values are known. Using these two you have to find out w value. Okay, and once you find w value, for future prediction you have w values, you have x values, you can find out new y values. Okay, that is how the process of training and prediction works. Now coming back to determinant. Okay, this was our topic. Now, in all of these system of linear equations, matrix multiplication, how does determinant come into play? That is what we want. We want to understand determinant, why it is used, how it is used, what essentially it means by having a determinant. Okay, that we will find out. Now, for a matrix 2 by 2 matrix A B C D, determinant is nothing but AD minus BC, right? So you just multiply the diagonals and subtract the non diagonal elements, which is in this case 2 into 3 is 6 minus 0 equals to 6. Okay, Fine. Now when you represent, let's just say you have a matrix with values 2 comma 0 and 0 comma 3. Okay, so the way how these are represented in the form of a plot is, you always take the starting point as origin. From origin you go up until 2 comma 0, and here again from origin you go up until 0 comma 3. So then this will form one vector, this will form another vector. Okay, for these vectors a combination of vector is a matrix. For these matrix you calculate the determinant. Now that determinant is nothing but the area of that particular vectors. Okay, i I can show you this here. Let's just say you have point 2 comma 0 from 0 comma 0, and again you have point 0 comma 3 from 0 comma 0. So if you have these two vectors, and if you draw parallel lines to, or the opposite lines to the opposite sides, or the perpendicular lines to the vectors, respective vectors, you will get a square or a rectangle. And the length of this, length is nothing but norm. Okay, length is nothing but norm of the vector. So this length is represented by 2, because the length is 2 here, here length is 3. If you multiply 3 twos are 6, you will get, and that is same as your determinant, no? So determinant essentially is nothing but the area of the vectors, the area created by the vectors. Another example, let's have a look at another example. You have another vector called 2 comma 3, and another vector called 1 comma 3. 2 comma 3 is point 2 and 3 on y axis. So this point, from origin you draw a line, and 1 comma 3 is here 1 on the x axis and 3 on the y axis. You draw another line. When you join this, you have to draw parallel lines to the opposite sides. You will get a parallelogram. Now, if you did calculate the determinant of this parallelogram, you will get 3, okay, which is same as the area created by this parallelogram. So when a vectors create a area, we say that those two vectors are linearly independent. Okay, two vectors are linearly independent if they form a area, if they form a rectangle or a parallelogram, and we can calculate the area. Two vectors are said to be linearly dependent if their area between them is 0. For example, these two vectors here, both these vectors are 2 comma 3, are overlapping with each other. If you pay attention, this second vector is a multiple of first vector. Okay, hence they are overlapping. When they are overlapping, they don't create any area, hence they are called as linearly dependent variables. Okay, I hope this is clear. Likewise, you can calculate for 3D also, three-dimensional vectors also. You can calculate the areas, and you can calculate the determinants separately, and you will notice that the area is nothing but the determinant value. Okay, so that you have to understand. If this is clear, we can stop here, and we can continue with the system of linear equations.